by actually showing you a schematic from a paper by Gareth McKinley and Tam Sridhar in the annual reviews of fluid mechanics. And it kind of explains what we've been doing so far, right? And if you start at the bottom, can you see clearly? No? Maybe it may make sense if I do that. Is that better? Yeah. So they are considering polystyrene and doing this kind of coarse graining procedure that we've followed. So you can see in a polystyrene of a certain molecular weight, the number of monomers that they have identified, the bond length of each monomer, and what the end-to-end distance would be at equilibrium. C infinity times NL squared. C infinity is the stiffness factor, and it's around 10. That means you have to go roughly 10 of these monomers before things become uncorrelated. And then you replace it by a freely jointed chain, right? And here you see you're doing this, trying to keep the end-to-end vector and the length the same, and it turns out you need something like 2885 cone steps to represent this in a cone chain, each which is about 12 of these monomers long. And finally the bead spring chain then coarse grains further, right? You lump several of these monomers and then make them into beads. So put the mass into a bead, and here we are now down to about 225 beads connected by springs, and they're talking about a relaxation time here, which I'll discuss tomorrow. And finally it's coarse grained all the way to a dumbbell. Okay, so just a single spring and two beads, and you can make predictions for this model. Okay, so we stopped here this morning, and I'm now going to actually simplify further to the level of a dumbbell, and then I'll do the algebra for dumbbells. Okay, and the idea is finally to get a constitutive equation for a dumbbell model and to relate it to a Maxwell model and so on, and to show you, which was what I began by saying, how does one get material functions by doing kinetic theory. And later on tomorrow I'll also talk about bead spring chains, but there we won't do much algebra because you'll spend all the time doing that. But because we've done it for dumbbells, it will be clear what we are doing. Okay, so we are going to start with a dumbbell model. So this is just two beads connected by a spring, and with respect to an origin, this is bead 1 and bead 2, so this would be R1 and R2, right? The connector vector connects these two, Q, and the center of mass will lie on this connector vector, and that is RC, and we define RC as 1 over 2 R1 plus R2, and Q as R2 minus R1. Okay, so the bead spring chain has now been reduced to the simplest version possible, and because it's a Gaussian distribution, the distribution for the connector vector psi q, maybe I should start, give myself more room, was h by 2 pi kbt all to the power of 3 over 2 minus h 2 kbt q squared. Okay. So that is the distribution function for a dumbbell. Now what we want to do is start considering flows and beginning to worry about rheology and developing constitutive equations. So almost all of kinetic theory as it stands has been developed for what are called homogeneous flows. Okay. And these are flows where the rate of strain tensor is independent of position. In other words, it's the same wherever you are in the flow field. Okay. Examples include simple shear flow, extensional flow, and so on. You see, the point is that most complex flows encountered in industry and so on are some combination of shear and extension. And the belief is if you can understand behavior in shear flows and extension flows, you should be able to understand generally behavior in more complex flows that are combinations of these, right? Also, the idea that the strain rate does not vary in space is not really as stringent as it appears, because what you're really talking about is how much does it vary over the length scale of a molecule, because you're writing this whole theory down on the molecular scale, and you want the strain rate to be uniform around the molecule, and that doesn't necessarily mean your velocity gradients in space are absent or don't depend on space. Okay. So let's now imagine we have a coordinate system x1, x2, x3, and you denote a position by r. This is the position vector of a point. Let's say the origin has a velocity v naught, and at this position r you have a velocity v at the position r, right? Now you can always write a Taylor series expansion for the velocity about the velocity at the origin. So if I write it in component form, if vi is my ith component of velocity, then I could say it's v0 plus del vi by del xj sum over j evaluated at the origin times xj plus 1 over 2 factorial sigma j sigma k del vi by del xk del xj xj xk plus so on. So this is just a multivariable Taylor series expansion. If your strain rate doesn't depend on space, remember we define gamma dot as grad v plus grad v transpose, right? And so in index notation, we could write grad v transpose, for instance, is del vi by del xj times ei ej, where these is a dyadic product of unit vectors. Okay. So if this is independent of space, then if you take its derivative, it's going to be 0. So which means this term and all higher order terms will be 0, they don't vary with space. And if we denote kappa as grad v transpose, then you can write your velocity back to vector notation as v naught. Oh, I should say this is v V naught I, right? It's the ith component of the velocity at the origin. Then this is just V naught plus kappa dot r. That is the velocity at any location r relative to the origin, because the flow is homogeneous, where kappa is your transpose of the velocity gradient. So, if I were to write it in matrix form, I would say Vx is kappa xxx plus kappa xyy plus kappa xzz. Vy would be kappa yxx, kappa yyyy, yzz, and Vz would be kappa zxx, zy, y. Right? That's the matrix representation. Oh, and I have left out the V naught. So, for simplicity, at least for these arguments, we assume V naught is 0. This is not a serious approximation or anything. It just, if you begin to translate relative to the local velocity, then anyway V naught will be 0. It just depends on the velocity of your frame of reference. So, now can you tell me what the equation of continuity is for an incompressible fluid? Del dot V is 0, right? Del dot V is 0, which could be written as trace grad V is 0, right, equivalent, and or it also trace of grad V transpose will be 0, which implies that trace kappa is 0, okay, and which means kappa xx plus kappa yy plus kappa zz is 0. So, the condition of incompressibility when applied to a homogeneous flow implies you have to have this condition. Okay, let us look at some simple examples. Okay, so how does one define simple shear flow? It's defined as Vx is kappa xy gamma dot, Vy is 0, Vz is 0. This is sorry, kappa xy y. This is the flow where you have a flow field like this, right? This is the x direction, that's the y direction. So, there is no flow in the y direction, there is no flow in the z direction, the only component of velocity is in the x direction, and kappa xy is your shear rate gamma dot. Okay? And you see all other kappas are 0, and you satisfy the trace kappa equal to 0, because all the diagonal components are 0 anyway. And now, let us look at so this is a homogeneous flow, and you can apply kinetic theory ideas to it, right. And then there is also what is called a shear free flow. Okay. Shear free flows are which have no rotational component in them. Elongational flows belong to this class of flows, but you can write more generally that an example would be Vx is minus half kappa zz times 1 plus b. Okay, Vy would be minus half kappa zz 1 minus b, and Vz would be kappa zz times z. Oh, I am missing x, y. So, if you now see, these are only diagonal components, right. This whole thing is kappa xx. This whole thing is kappa yy, because it is the coefficient of y, and this is kappa zz. So, if you add them up, you will see that trace kappa is 0, So, you are satisfying your incompressibility. By the way, B is a number that lies between 0 and 1. Okay. If it is 0, you get uniaxial extensional flow and so on. Different kinds of elongational flow you get for different values of B. Okay. And we denote typically kappa ZZ is epsilon dot, your elongation rate. So, these are the kinds of flows we are going to consider, and we are going to derive a kinetic theory for such homogeneous flows. Okay. So, this morning we looked at equilibrium distribution functions. And now what we are going to do is look at non-equilibrium distribution functions. Okay. And now in the morning we talked about P1 being the momentum of bead 1, P2 being the momentum of bead 2 and so on, and we had connector vectors Q1, Q2 so on for our bead spring chain. Now I am going to do this whole development as I said for dumbbell. So, we have only P1, P2 and Q, okay. But it turns out for non-equilibrium distribution functions it is actually convenient to work not with the momentum but the velocities directly. So, R1 dot, R2 dot and Q. So, we would write for instance that RC dot, the velocity of the center of mass, would be half R1 dot plus R2 dot, right, for the velocity of the center of mass. Now, we are going to talk about a general non-equilibrium distribution function f, which is a function of the velocity of the first bead, of the second bead, of the connector vector q and time. So, we are going to ask, so if I were to multiply this by dr1 dot, dr2 dot, dq, this quantity gives the probability that bead 1 has a velocity r1 dot, bead 2 has a velocity r2 dot, and the connector vector q has a magnitude or vector is given by q at time t, because it is non-equilibrium, it can evolve in time, right. And now this we are going to say is normalized. In other words, dr1 dot, dr2 dot, dq of f of r1 dot, r2 dot, q comma t is equal to 1. Now, if I want the equilibrium distribution function psi, the configurational distribution function psi, non-equilibrium. In other words, psi is a function of both q and t. I say, well, just integrate out the dependence on velocities from f, and that is how I define this psi. And you can clearly see if I integrate psi of q comma t dq, then I have to integrate the right hand side as well by dq, and that is the normalization condition on f. So, this is also normalized. Okay. So, that is equal to 1. It will prove to be convenient for me to define a momentum space configuration, a distribution function, which is a function of r1 dot, r2 dot and in fact q and t, and is defined by f of r1 dot, r2 dot, q comma t divided by psi q comma t. Okay. Right. So, often we assume that this psi is Maxwellian about the solvent velocity field. What do I mean by that? That it actually has this specific form, e to the power of minus 1 over 2 sigma nu equal to 1 to 2 of m times r1 dot minus v squared plus r2 dot minus v squared divided by the integral of this, which is the normalization, or the essentially the partition function in velocity space. You will recognize this, right, as Maxwell's velocity distribution for a system of gas particles, for instance, in statistical mechanics. At equilibrium, they obey this. This assumption we make in polymer kinetic theory is, of course, that the molecules are being translated along with the solvent with the velocity v, but about that they have a equilibrium distribution function, and it's called there's a phrase for this assumption, it's called equilibration in momentum space. It's basically a Gaussian distribution, and we are interested in configurations of the molecules, right? And we have argued that all your rheological properties have to do with configurations of your molecules. So we are interested in how those configurations change in space, right? And it turns out that the time scale on which you have spatial motion is much slower than on which you have changes in velocity space. So the dumbbells will very quickly equilibrate back to their equilibrium distribution in terms of R1 dot and R2 dot, but Q will take longer to reach equilibrium if you disturb it. That is the idea behind this. Okay. So yeah, so we'll it depends on what you mean by very strong. So people have relaxed this equilibration in momentum space and try to understand, and you have to be really violently disruptive, and this happens on much yeah, it's a matter of time scale. So you have to see what time scale is my, it's always relative to the time scale in which my configuration is changing, and so if you have a high velocity gradient, that means a very small time scale. And then you have to look at what is the corresponding length scale that time scale corresponds to, and then see if your changes in your configuration space are happening in that very short time scale. Okay. So I think it's a reasonable assumption under most circumstances, but if you are looking at an extreme situation, then you have to be aware that there is an underlying assumption that's being made. Okay. So we could write f r1 dot r2 dot q comma t as the product of this psi just by the definition of psi times psi of q comma t. And like before, we can start talking about averages, right. So B, the average of B in general is written as dr1 dot dr2 dot dq of B times f r1 dot r2 dot q comma t, right. This is the general definition. Now if I plug in this product here, right, in for f, then I can do the integral over dr1 dot dr2 dot and psi, and that would be nothing but so first let me define that. Okay, I need to define a momentum space average is integral dr1 dot dr2 dot b times psi. Okay. Once I have defined this, then you know I can always break up this f into psi times psi and then combine this part of it, so that B would then get written as integral dq B psi, okay, of q comma t. The difference between what I was doing this morning is that I am not sticking an equilibrium as a suffix to everything, just to distinguish that this is now evolving in time and it is away from equilibrium. Okay. And of course, if B is only a function of q, then this implies that here B is the same as this, because it does nothing to it, right. If you look here, B would come out of this integral and then you would just get a normalized term, and therefore B is integral B of psi q comma t dq, when B is only of, so maybe I should make that clear. Okay, so that's the basic background that we need now before we start talking about the stress tensor. So finally we are coming to rheology. Okay, so let's talk about the stress tensor. Now I want to remind you of an important continuum mechanics result. As you are aware, what is the stress? The stress is force per unit area, right, and it is essentially a surface force. Now at a point, right, how many surfaces pass through a point? Infinite number of surfaces. So when we specify a surface force, we have to say what surface is it acting on. And so what we normally do is, when we have a surface, we will always give the normal to that surface, because the normal to the surface specifies the surface. If the surface rotates, the normal rotates. So if I know the normal, I know what surface I am talking about. And I am usually interested in what is the surface force, and we usually call it the traction vector, right, force per unit area. What is the traction vector acting on an arbitrary surface whose normal is in the direction n? Now I guess you would have learned in continuum mechanics that this sigma t is nothing but n dot pi, okay, where this is the stress tensor. So the beauty of the stress tensor is it's essentially a storehouse of information. It's a matrix that contains some data, and if you dot this tensor with the normal that you are interested in, it gives you the traction vector on that surface. So you do not have to store infinite information about all possible surface forces. All you need is this one stress tensor, and then you can find the force on any surface. So for polymer solutions, we are going to write that the total stress is a sum of two stresses, one coming from the solvent and another coming from the polymer. Now what is the basis for this? There is none. Okay, I mean, I do not think one can justify it from some more deep fundamental argument. It is just an assumption that the stresses add up, I mean combine additively. Okay, and so we know that the solvent contribution, which is usually assumed to be Newtonian, is minus eta s gamma dot. I should first, so there is a pressure term, okay, isotropic pressure term from the solvent. Now this delta is the Kronecker delta, right, or identity tensor, which is the same thing, and the components are the Kronecker delta. Yes, sir.
This was always in my mind. Did someone actually think of this assumption that, when will this break down, and is there a possibility of breakdown?
I actually haven't seen any literature justifying it, or maybe back in, I have to go back and look at Bird and see if they talk about it at all.
I don't think
I can't, no, they don't. So, even at the level of this kinetic theory, right, it's an assumption. So if you think about pressure, right, which is the simplest force per unit area. So you have a, let's say, a surface with your polymer solution on one side, and we know from kinetic theory or statistical mechanics that essentially the pressure is the change in momentum of these molecules that are striking and going back, difference in momentum, that's the pressure. So the assumption is, okay, the polymer comes and strikes and goes, and the solvent comes and strikes and goes, and then you have to just add all of it, and that's the pressure. And I'm assuming that's the basis for this additive. Yeah.
It's just so simple an assumption.
Some things are axiomatic, right? It's almost as if you have to say this is it, and only then can I proceed, otherwise I can't. And I think this is almost at the level of an axiom. And so then you add the pressure, isotropic pressure from the polymer. Yeah. Yeah. Yes, but so it's interesting. I will show you a little tomorrow, but I can't go into serious kinetic theory. But we do consider, for instance, excluded volume interactions between segments of the polymer chain, or hydrodynamic interactions that are mediated through the solvent and so on. So the solvent is doing something to affect the polymer configurations and therefore changes the stress. So you could think of it as the solvent being essential for that physics. But at this level we still treat them as independent, and all the interactions that are coming are happening within this pi p already, even if there are interactions due to the solvent. Okay. Yeah, I mean, I think that's beyond the scope of what we are discussing today. That might be a research topic. And then we have to add what's called the deviatoric part of the stress tensor, what is left over after you've removed the isotropic part. Okay. So now the question is, how can we find this pi p, okay, this polymer contribution to the stress tensor. And this was intuitively sketched out by Kramers. I can't remember around when he did this, and we will follow his argument to derive what this pi p is. And essentially, remember that the stress is force per unit area, and the reason you can have stress in a polymer solution, because there are polymers in it, according to Kramers, was twofold. One is you can have a polymer that is straddling the surface. So you have a surface and one part of the polymer is on one side and the other part is on the other side, and there is tension in this because you are stretching it, and that leads to a surface force. Okay. The other is you have these polymers just traveling across the surface, carrying their momentum across. So when they take momentum from one side to the other, they contribute to the surface force, because you can think of momentum flux as the same as a surface force. In your transport phenomena, I hope you've seen the equivalence of either a momentum flux or a surface force. They are equivalent. So there are these two mechanisms, and what we are going to do is actually sketch out how we can calculate this. So maybe we should write here straddling a plane, mechanisms, or crossing the surface. So let's treat this case first, and I'm going to have to sketch something. So here's a box. Okay. I'm not very good at this, so okay. And let's consider this surface. we will say it has got a surface area S, and we will say the normal to the surface is n, and I am going to call this side positive of the surface into which n points, and the other side negative, and I am going to assume this bead 1 is inside and this dumbbell spring comes out and bead 2 is here. So, we want to know what is the total contribution to the force per unit area because of this situation, okay, and I must draw the unit vector, the connector vector q as well. Well, because n and q are in the same direction, in this case n dot q is going to be 0 for the situation that I have drawn. Okay. Now, we can ask how many such dumbbells are there. Now, first I have to introduce that NP is the number of dumbbells per unit volume. Okay. So, how do I find the number of dumbbells? Well, I must know what is the volume of this box. And then if I multiply it by the number of dumbbells per unit volume, I would get the number of dumbbells in there. And so, that is basically the volume of the box is n dot q times s, because n dot q is the projection of q in the direction n, times s is the surface area, that is a volume. Okay. I have to multiply it by psi. You can think of this as a density, right. The property is essentially the same as the density. So, if you multiply or the number density, number per unit volume times the volume times NP would give you the number of dumbbells in here. Okay. Now, we want to know what is the force that is being contributed per unit area because of this situation, and for that it is helpful to think of it like this. So, I have this is my negative side, okay, and this is my positive side, and what I am saying is I have a situation like this where this is bead 1 and this is bead 2. So, we all know that this force I am calling F1 phi. Well, we all know, this is the first time I am talking about it. So, you might know already, but you should not know. So, F1 phi is this force in the spring, and there is an equal and opposite F2 phi because of bead 2, okay, in the spring. So, let us firstly say something about this F1 phi and F2 phi, and I will write in the next page. If phi q is the potential energy of the chain, right, we know that the force due to this potential is defined as minus del phi by del r nu, where nu is your bead index. So, F1 would be del phi by del r1, F2 would be del phi by del r2. But phi is a function of q. So, if you wanted to find for instance del phi by del r1, it would be del phi by del q dotted with del q by del r1, and del phi by del r2 would be del phi over del q dotted with del phi over del r2. Okay. But we know that q is r2 minus r1. Okay. So, del q is wrong, right, q. I thought I saw a smile somewhere there in the audience, and so you are just testing me, of course. How long will you keep making that mistake? Okay. So, del q over del r2 is 1. Well, it is actually the unit tensor delta, and del q over del r1 is minus delta. Okay. So, in other words, del phi over del r1 would be minus del phi over del q, and del phi over del r2 would be plus del phi over del q. Okay. So, going back to our definition of f1 and f2 phi. So, that means f1 phi minus del phi over del r1, and therefore, it is plus, and f2 phi would be minus del phi over del q. And we are going to call this connector force Fc as del phi over del q. So, that F1 phi would be Fc, and F2 phi would be minus Fc, which is also minus F1 phi as we expect. Now, of course, if you know, so shall we look at the simple case where you have a Hookean dumbbell, since we are here, and we say, well, phi is half h q squared, quadratic spring, right. So, then del phi over del q is simply h times q. So, this is and which is what your connector force will be. This is the Hookean spring force with a spring constant h. Okay. So, all this background now for explaining what was this F1 phi. Now, we have to ask what is the force, right, that the material on side 1 or on the negative side is exerting on the material on the positive side. So, the way to understand this is we replace this negative side by some kind of continuum like this, right, and what would happen then, you see F1, there is a tension F1 phi pulling the spring, right. If I completely replace this by some kind of material, then side 2 has to pull this negative side with that F1 phi, that is what it means, right. The spring is effectively doing that. So, if we want to know what is 1 doing to 2, or sorry, a negative side doing to the positive side, it is pulling back with minus F1 phi. Okay. So, that is effectively what the negative side is imposing on the positive side, and so we have to, this was the number of dumbbells in there, we now have to integrate, multiply it by minus F1 phi and integrate over all these possibilities where, so I am going to integrate all of those where n dot q was greater than 0. This immediately means 1 is on the negative side, bead 1, and bead 2 is on the positive side. So, this was NP n dot q, right, times, now I will remove the s because I am going to talk about force per unit area. So, I will divide by s times the probability that you have the connector vector q over there times minus F1 phi, right. This is the total contribution from, if I integrate over all of these, that means all possible q vectors such that 1 is on this side and 2 is on the other side. That is the contribution. There will be exactly, now I can do the same argument, put bead 2 in the negative side and bead 1 on the positive side, and you will just have to believe me. So, this one will be n dot q, and you can work this out for yourself. This is n dot q is less than 0, n p, and now the volume, to keep the sign, will be minus n dot q times, sorry, this is not n, this is n p times psi q comma t, and we will get a minus F2 phi for the same reason as before, dq. Okay. Now, if I replace this by minus F c, okay, and this by plus F c, because F 2 was minus F c, then you see the integrands are the same. There is a minus here and there is a minus here. So, both the integrands are same, only here you are doing over positive n dot q, negative n dot q. So, then you can get rid of this positive negative and just combine it all under the same integral. So, this will be equal to over all q dq psi q comma t, there is an np n dot f n dot q, sorry, times f c. Okay. So, I am going to now introduce a tensor which I will call pi p due to these connector vectors straddling the plane, and I am going to define it as minus n p integral dq psi q comma t q f c. Okay. So, this force per unit area can be clearly seen to be minus n dot, this is nothing but the average of q f c, right, because that is how you define an average, this is how we defined it. So, this would be n dot q f c, or is yeah, minus n dot, there is a no, the minus, sorry. So, the minus is coming from here. So, there should be a minus here, and I have absorbed that minus into my so this is still this way, right. Right, but now there is a n dot pi, and this should be, is that okay? Any errors? All the algebra good? Okay. So, we have found what the stress tensor contribution due to a dumbbell straddling the plane. Now, we need to find the second contribution, and which is the following, and again we will use a schematic representation. So, I got a box, maybe I should make some comments here, I will wait. Okay. So, I have a box, and I hope I will remember to make them later, but I think it is appropriate to and let us say this has a surface S, and there is a unit normal n, and now we have got this one bead here connected to bead 2, this bead 1, and this is traveling with velocity r1 dot, r2 dot, and relative to the solvent we will say minus v over here, minus v there. Okay. We want to know how many of these 1 beads is crossing this surface, because it is taking momentum with it, and then how many 2 beads are crossing this surface. and then we will add up this momentum together, and that is going to be another contribution to the stress tensor. Okay. So, how do we calculate that? I always find it. So, firstly, only dumbbells where the velocity is normal to the surface will go through, right. The component of velocity that is tangential to the surface will just lead the dumbbells to stay inside the box. So, we only need to consider those that are normal to the surface. So, let us imagine that you have this surface, and I say let us go backwards from this surface for a distance whose magnitude is r1 dot minus v dot n, okay, just for argument's sake. That is the projection of the velocity in the normal direction, and we have gone back from this surface, right. Now, this is the velocity, right, times delta t will be the distance travelled by these bead 1 in time delta t. So, if you consider any beads that are outside this box in time delta t, because they have gone r1 dot minus v dot n times delta t, they will not reach this surface, because this is that distance, unless they are within, anything within that will go through the surface, anything outside will not make it in time delta t. So, if I want to know what is the flux of beads 1 that have gone through this, it is all of these, right. This is the distance times the surface area, that is the volume, everything in this volume. So, I would say r1 dot minus v dotted with n times s times delta t, that is a volume times the NP, number per unit volume. All of this is the flux in time delta 3 at t going through the surface, and they are carrying what momentum? Well, their momentum is r1 dot minus v, that is the amount of momentum they are taking with them. Okay. But I want to know the flux. So, I divide by unit area per unit time. So, the flux of 1 beads through surface S, if I now integrate over all possible velocities and connector vectors and so on, I take the average of this. But before I do that, they will be identical from r2 dot, right. I can make the same argument, that is of ditto of 2 beads through the surface, right. And now, if I add these two and average over all of them that went, so it would be integral dr1 dot dr2 dot dq f times sum of nu equal to 1 to 2 of well, the m can come outside, r1 dot minus v times r1 dot minus v plus r2 dot minus v. Do you see that? Okay. Now, you recognize that this r1 dot multiplied. So, this can be broken up into psi times the momentum distribution function times the configurational distribution function, and I can do the integral of these over the momentum distribution function, and so this would then become integral dq psi of q of m sigma nu equal to 1 to 2 of I have got the m. Okay, let us take Okay. And if we now make the okay, so am I missing an n dot? There's an n dot, right? It's n dot this whole thing. Yeah, because of this dot n. And I'm going to define my pi p, and we call this b as this integral of this thing. Okay, so that the contribution per due to this would be n dot pi p b. I'm not 100% sure about this algebra. I will check it and tell you. I have this vague uneasy feeling I may be wrong somewhere. But this is the general idea. Now, if you do, if you assume equilibration in momentum space, then you can show that this pi p b, because essentially you have to do this average, right, over here, and that this momentum space average, if you know that the distribution function is Maxwellian about the solvent velocity, that is essentially a Gaussian distribution. So, you can actually work it out and it will turn out it is just 2 np kb t delta, that is it. So, in other words, it is an isotropic contribution to the stress. Now, do you know if isotropic contributions to stress contribute to rheological properties? No, because you know that, for instance, the shear stress is only an off diagonal component. So, this will not contribute, right, because it is a diagonal component. Secondly, you always measure differences in stresses, normal stresses. That is why you have the first normal stress difference coefficient, second normal stress difference coefficient, because there is no way you can separate, when you have a normal force on a surface, what is the pressure contribution and what is because of the deviatoric part. All you will measure is a normal force. So, you have to take the difference between two normal forces to get rid of that pressure part, okay, and that is why isotropic contributions are never taken into account. So, we know this now. So, I could then say that the total pi p was minus, no, did I have a minus sign? I can't remember. I think it had a minus, right? Yeah, minus np q fc plus 2 np kbt delta. Okay. Now, which means that the total stress pi is ps delta, okay, okay, plus no, minus eta s gamma dot minus np qfc plus 2 np kbt delta. So, the equilibrium, sorry.
So, there are two terms in that phi p. So, the second one is the thermodynamic contribution or equilibrium contribution.
this 2np kBt delta.
And the first term also has an isotropic property.
The first term has, you mean if has a diagonal component.
Yeah. So
Yes, but it will contribute to stress differences. It is not a unit tensor. You are right, but so you will have to take differences, and so if I
that corresponds to normal stress difference.
yes.
And only the deviated part actually is not for the other.
Well, this one will contribute to, you will see, and that is just what I am coming to. We are going to identify the deviatoric part. Okay. So, what is the deviatoric part? How is it defined? Tau is pi minus pi equilibrium, right? If you subtract away what is there when there is no flow, is what is the deviatoric part. So, what is pi equilibrium now? Now, you have to accept this result for the time being, that QFC at equilibrium, the equilibrium average of this is nothing but kBt delta. Okay. Now, if we will derive this tomorrow in as a kind of supplementary result to something else that we are doing. So, you will have to believe me when I say this, but if you are really eager to prove it for yourself, then just substitute the Hookean force in here for Fc, just HQ, and go and carry out this integral with the known Gaussian distribution function, and you will see this is the case. Okay, if you want to check that, but if you believe me, then this is nothing but Ps delta. The gamma dot is 0 at equilibrium, right? Minus Np kBt delta plus 2 Np kBt delta. In other words, this is Ps delta plus Np kBt delta.
So when you write tau is equal to pi minus pi equilibrium, so tau is the threshold into the whatever flow of the fluid, right?
Stress.
Right. Now the total pi, the first term that you write, that is the total stress transfer during flow, and the second term is during no flow. Right. So the pressure in both conditions may not be the same. So how can you say that?
No, no. You define pressure as the static normal force in the absence of flow. So, I would say this pi equilibrium is Ps delta plus Pp polymer contribution times delta, whatever is left. That is how you define it.
Can I give an example? I don't think it would be applicable.
Okay.
So recently I was doing a project in that simulate flow around the sphere.
That we have to talk about later if we are going to get into that kind of detail. Okay.
So when there is no flow, pressure is completely asymptotic around the sphere. But when I give the entire fluid a velocity in my direction, I see a pressure field around the fluid.
Yes, of course.
So the pressure is not the same in both cases around the fluid, right? In the fluid.
Right. Okay. So, there is a difference there. In the second case where there is flow, that pressure is not a thermodynamic pressure. Okay. Yeah. We have to talk about it later. But you are right, obviously it becomes a pressure field, but that is not thermodynamic. Yeah. Yeah. So, here you would have to write an equation of state. That would be a thermodynamic pressure. Okay. It is subtle, but yeah, it is worth talking about. It is a good point. So, now where was I? So, this is Np kBt delta. Okay. And so, then tau clearly, if I subtract this away from this whole thing, is nothing but minus eta s gamma dot minus Np QFC plus Np kBt delta. So, it completely comes in the deviatoric part. Okay. So, there are a couple of things I want you to recognize is that, so for instance we can write, see the connector force is in the direction of the connector vector. So Fc, how are we doing for time? We are okay, right? When we started at 2:10 or so, so we have a half an hour. Okay, yeah, fine. Yeah, I should be okay. So this can be written as the magnitude Fc times the connector vector q, right? Because divided by the so by the unit vector in the direction of q. So this q mod is the magnitude of q. If I divide the vector q, then it's the unit normal in the direction of q times the magnitude of the force. So we can see that even in general the deviatoric stress would be minus eta s gamma dot minus np times q q f c over mod of q, that is just a scalar, this whole thing, plus np kbt delta. So what does this tell us about the tensor tau, this form? That it is symmetric. You see, because gamma dot is a symmetric tensor and q q is symmetric, and so this implies that tau is symmetric. So this kinetic theory automatically gives you a symmetric stress tensor. And if we have a Hookean dumbbell, then we saw that Fc was just h times q. So then tau would be minus eta s gamma dot minus np h times q q, right, plus np kbt delta. This is the famous Kramer's expression for the stress tensor. And now for the first time we are seeing what was all this stuff I was saying about the conformation of molecules being responsible for rheology. The QQ is a molecular detail. It is the connector vector of the molecule averaged over all molecules, and that is responsible for the macroscopic deviatoric stress.
Sir, this won't give us normal stress differences. The Hookean,
Of course it will give, you won't.
the second term.
Okay, yes, I mean in a simple shear flow the simplest model will lead to zero normal. No, you will get the first normal stress difference is non-zero, the second normal stress difference is 0. We might actually tomorrow work out this, so be patient.
What I'm saying is that the prefactor eta ph, that is constant.
NPH, yes.
NPH is constant, and this is QQ is like.
So what are the diagonal components? Qx squared, Qy squared, Qz squared. Only if they are the same will their difference be 0. It will turn out in simple shear flow it is not, and that is why it contributes to a normal stress difference. That is the, I mean if it was 0 normal stress difference, this is a Newtonian fluid, then there is no point in this entire exercise, right. And so that is the first useful thing we have got out of this, is it captures that elastic contribution that the normal stress difference is non-zero, right. That is and so it is good you asked me that question because it gave us an opportunity to discuss it. Okay, so we have seen now how molecular configuration is related to macroscopic rheology. But what does this tell us? If you want to know what this macroscopic stress tensor is, then we need, because what is QQ average? It is integral QQ psi q comma t dq. So, in order to evaluate this average, I need to know this distribution function, non-equilibrium distribution function psi as a function of q and t. So, that is given by something called the diffusion equation. No, the gamma dot influences indirectly. There is a strain rate because you put the polymer in a shear flow. It affects it stretches the chain, it changes Q, and that is why you get a stress. Yes, that is where the stress is coming from. Yeah, that is essentially.
And how is symmetric that result is in line with the classical mechanics?
Of course, for classical mechanics, if you have angular momentum balance, it automatically implies that the stress tensor is symmetric.
Assuming there are no point couples.
Exactly.
Then here
Yeah, we didn't have any such. We don't have charges and a force field on it that could lead to local couples, polar molecules.
when we didn't take them into account, that is the reason that we can cover.
Yes, it makes sense.
Does this model indicate anything about the magnitude, I mean, like whether it is positive or negative, or will it say that this is going, N1 is going to be positive or N2 is going to be?
The normal stress difference. No, not at this stage. It does in fact come later, but I mean you would have to be really clever to look at this equation and arrive at that. I will show you, and it will be tomorrow. We will work through this for simple shear flow, and you will see what the material functions are, and then you will see it predicts a 0-second normal stress difference, and gives you a precise expression for the first normal stress difference.
Which will give a rating positive.
It is positive. Yeah.
If we get to have any point couples, can you make a couple of comments on how?
We'd have to redo the kinetic theory. We'd have to go back and put it right in the beginning and account for it. Maybe in what I am going to do now you might see that, because in order to derive a diffusion equation, and I might run over time, we have to write two components, an equation of motion. This needs what is called an equation of motion and an equation of continuity. Okay. So, let us take the equation of motion first, which is just a momentum balance, a sum of forces, and we are going to say that the bead contribution due to the beads, the mass is so small that you can drop the inertial term. So, we say 0 is equal to sum of all the forces, that is there is no acceleration. We say there are the following forces. The first is a force due to hydrodynamic effects, and then there is a force due to Brownian effects, and then there is a force due to the potential, and finally there could be an external force due to various reasons. Now, I still do not know if your question comes in here. It does not, because this is, you have to see at the time when we were drawing those dumbbells straddling the planes and so on, you will not get a simple thing then, maybe because there will be non-local couples. Okay. And so, I am going to write the form for each of these. So, the hydrodynamic drag force is considered to be the friction coefficient of a bead times, this is the velocity of a bead, average, suitably average, minus, now I am going to write this like this, V nu plus V prime nu. Sorry.
So these polymer molecules which are modeled as bead and strings, so like this the application of shear, they align mostly in the flow direction.
So I am going to have to stop you, because I would love to answer, but we need to have an open ended final time. I am happy to stand outside and chat for as long as you want, but I am not going to be able to finish what I want, and then we will fall short tomorrow as well. So, keep it in mind, write it down, catch me, and I am here for the whole week, but we will resolve it. Okay, but I can't do it right now. Okay, so we are saying the drag force is the difference between the bead velocity and the solvent velocity, and that is what V nu is, the velocity of the solvent at the bead nu, right. But I have got a correction here which I am calling V prime nu, and what is that? That is what is called hydrodynamic interaction. Okay, so if I have a chain and one segment in the chain moves, it disturbs the solvent in the vicinity of that segment, and that disturbance in the solvent velocity field propagates to other segments and changes the local velocity around another bead. So, this V prime nu is what is the disturbance to the velocity because some other bead somewhere was moving. Okay. So, this is how it affects the drag force. In the simplest model that we are going to look at, we are going to drop this term because Rouse did not treat hydrodynamic interactions. So, you might have heard of the Zim model, which is the improvement of the Rouse model. There you treat hydrodynamic interaction. So, tomorrow if I have time, I will look at what happens when you keep this term, but for the time being we leave it there as the general expression, and then let us consider what this F nu, the Brownian term, and this has the following form. And what this is not straightforward to understand, but you have to think of it in the following way. Okay. Now, you know that when there is a concentration gradient, you have diffusion, because you are trying to reduce the concentration gradient, and molecules which are in the region of higher concentration diffuse down to region where there is less concentration. So, in thermodynamics, the way you write it as a gradient in the chemical potential, it is because of gradients in chemical potential that you have diffusion. On a molecular scale, of course, you will have many more molecules of one kind than in another region, that is what you mean by a concentration difference, and molecules are going in all directions, but because you have more in one region, they diffuse and tend to level out the concentration, right. What you have to think of this is of a chemical potential in probability space. So, you know the chemical potential expression is kBT log of concentration from thermodynamics. So, here it is like kBT log psi. This is a chemical potential or a gradient in probability space, and what Brownian forces are doing is they are randomizing your configurations so that you are not in any kind of extreme state, they are reducing you to your equilibrium configuration. And so, this is the idea that you are diffusing in probability space to get rid of any steep gradients in your distribution functions. Okay? And that is the physical meaning of this. And then we have F nu phi, which we have seen of course, and this is minus del phi by del r nu. And finally, this is just the external force that could be for any reason such as a centrifugal force or a charge and so on. So, we are going to add all of these and write as 0 is minus zeta times r dot nu minus V nu. So, we will and this we can now write, it is the velocity at the location of bead nu. So, we saw how that was V 0 plus kappa dot r, right. So, minus kappa dot r nu, this is the solvent velocity at that location, right, that is the hydrodynamic force, minus kBT del log psi by del r nu minus del phi by del r nu plus F nu E. Okay? That is my force balance. And now, I can rearrange it to solve just for r dot nu. So, imagine I have just taken r dot nu over to the left hand side. Okay. then what will I get? R dot nu, okay, is V 0 plus kappa dotted with R nu, and then I have to have divided by zeta throughout. So, it will be minus kBt over zeta del log psi over del R nu minus 1 over zeta del phi over del R nu plus 1 over zeta F nu. Okay, is that clear? Of course, we can write this for bead 1 and bead 2, and that is what we are going to do next. But before we do that, I want to write everything in terms of connector vectors. So, if I have del log psi by del R1, remember psi is a function of either R1 and R2 and time or Q and time, right. So, this would be written as del log psi over del Q times del Q over del R1 plus del log psi over del RC. So, you can use either RC and Q or R1 and R2 as the variables times del RC by del R1. Now, this distribution function does not depend on RC, we said that right in the beginning, right. So, this goes to 0, and we saw how del Q by del R1 was minus delta, right. So, then this becomes minus del log psi by del Q. Okay. Similarly, we can show that del log psi over del R2 would be plus, because it is del Q over del R2 and that is plus. So, this would be del log psi over del Q. Okay. So, let us now write the expression for R1 dot and R2 dot, okay, from above. So, R1 dot is equal to V naught plus kappa dotted with R1. So, this was minus and this is minus, so it will be plus kBt over zeta del log psi over del Q, right. And remember, this was del phi over del R1 was minus del phi over del Q, right, which was Fc. So, this is minus 1 over zeta Fc. Am I correct here, or so we can just look at this as plus minus F1 phi, and so it should just be minus Fc. Yeah, that is what it is. Okay. Let me. This is always a pain when we write this. You see, I made a mistake because it's plus F nu phi. No, that's okay. Plus F nu phi was minus del phi del R nu. So, I have written it correctly. So, it's plus and should be, and only this term gets taken over to the left hand side. So, it's a plus Fc. Okay, plus Fe. And I can write the same thing for R2 dot. Let us just finish the equation of motion and then I will stop, and then we can do the equation of continuity and the diffusion equation tomorrow. So, this would be V naught plus kappa dot R2 plus kBt over zeta, and now this is minus del log psi over del Q, and this is minus 1 over zeta because it is plus F2 phi, and that is minus Fc plus Fe. Okay. So, now we can derive the equations of motion for the center of mass, because you remember Rc dot is 1 over 2 R1 dot plus R2 dot, and so that means I just add these two equations and divide by 2. So, you can see as I am doing that this is what it would give. You will get 2 V naughts, but you divide by 2, you get kappa dotted with R1 plus R2 over 2, which is nothing but RC, and then these two will cancel, they have the opposite sign, the log side terms, and the FC's will cancel because they have the opposite sign, but the other one will add up. So, you will get 1, oh there is a zeta here, over 2 zeta, no sorry 2 over zeta, 2 such terms. So, actually I need to distinguish F1 and F2, and so there is only, they are not 1 over zeta F1e plus F2e. So, what is interesting here is if you imagine there are no external forces acting on your beads, what is it telling you? R dot C is just V dot plus kappa dot RC. That means the whole dumbbell is just translating with the solvent velocity at the location of the center of mass. If there is no external forces on it, it is just undergoing affine motion. That is what we have just seen. Okay. And what about Q dot, which you know is R2 dot minus R, okay, let us write it, R2 dot minus R1 dot. Okay. If I take the difference between the two, what will I get? The V naughts will cancel, kappa dot. So, I am taking the second equation minus the first, R2 minus R1, and so that is nothing but Q. Okay. And then if I take the difference of these, that will become a minus, so I will get minus 2 kBt over zeta del log psi over del q, and then that will become minus in R1 dot. So, I will get minus 2 over zeta Fc, and finally plus 1 over zeta F2e minus F1e. Now, I am going to assume if there are any external forces that F1e is equal to F2e. They are the same on both the beads. Then this last term drops out, and we can finally write what is called the equation of motion for the connector vector, and this is a crucial equation that we need. Okay. So, that is going to take us halfway to finding the diffusion equation for the probability distribution side. We will stop here. I mean, because I mean the continuity equation will take another 10 minutes, I think. So, but tomorrow we will start with the continuity equation and get the diffusion equation and continue from there. But solve for this, sorry. Shear flow, I will then do the solution of a problem of simple shear flow, but there is a lot to learn along the way. So, at the end of these lectures, you should be able to read chapters 11, 12, 13 and 15 from Dynamics of Polymeric Liquids volume 2. You should really be able to follow it all, but I still have a way to go. Okay, thank you. There is the Kramer's Kirkwood expression, the Giesecke's expression. I will do Giesecke's tomorrow, and you will see that. Okay, but essentially this is the foundation. Once you have this, you can get all of them. There is nothing there that we don't know. Okay, thanks.